will kind of introduce what I will be talking to you about in the next week. So what you see here, if I switch this on, so what you see here is a bunch of networks, right? And you obviously know if you looked at the schedule from the title of my courses, that I will be talking to you about biological flow networks. So here you see some, let's say, representative examples that are obvious to you in nature, like a leaf. You see this slime mold Physarum polycephalum. You see here that's a vascular network from an animal. Here you see basically the lungs, but then you see some non-biological networks as well. Now, I won't get too much into this, but the reason I'm also showing you these guys as well is that actually with the stuff that you will be learning this week, you would be equally able to start thinking, posing, and maybe answering questions related to non-biological systems. The reason is that all of these systems, they have several things in common actually. One is that they transferred something, they transfer a physical load, and the other very important thing is that the flow at the nodes is conserved, right? There is mass conservation or material conservation or field conservation at the nodes, and that will be an important thing that will come up later. Now, you don't do introductions, but I will introduce myself, right? So I am from the University of Pennsylvania. Most of my work has to do with complex systems broadly construed and vascular networks, which is what I will be talking to you about, but also I have an interest in elasticity and pattern formation. In case some of you are working on this, I would love to talk to you about it. Now, this is a very concise overview of what we will be talking about, just to give you some feeling. By the way, you should be interrupting me all the time.
They will, don't worry.
They will, okay, that's just, yeah. Okay. So if you don't interrupt me, then I will start asking questions, and that is worse. So in the beginning, mostly in this lecture, we will be discussing the biology, right? How, what is a flow network in a living organism, right? Or as I call it, fun facts about living flows. Then we'll move on to modeling, actually how we can make all of these very complex things abstract and build the simplest possible model you can without any bells and whistles. Then we'll be talking about why do networks in nature look like they do, principles of optimization and evolution, and then we're going to ask how do networks actually build themselves, right? Yes, if it's a man-made network, you hire an engineer, they design it, you build it, but how does biology do it? Then, time permitting, we're going to be discussing about topology and graph theory, some very, very cool and generally applicable cool tools to quantify graphs. And last, and that is a very tentative, maybe we'll do pulsatile flow, nonlinear networks, mechanical networks, and anything else you might want me to do. Now, this is mostly going to be a blackboard talk, but you know, it's biology, you have to see the picture, so I'm starting with a slideshow presentation. But this is mostly the things you will be needing for this course. One is the notes. Now, I was, as usual, very late in preparing them, so they're not actually in the school's website, and that's only my own fault. It is, though, on my web page, and you can, it's a very, very, very out-of-date web page, so you just need to, you ignore everything else, you just go here, this is a place, this is where I stuffed it, you go to classes, you hover, and then you go to Boulder Summer School, and then you click and you get this document, which is basically what I will talk about today. So just throw your pencils, throw your notebooks. It's maybe 80-90% of what I will talk today, including some fun references that you can read if there is a particular topic that strikes your fancy. The references there, it's all, it should all be available through your university's library. If not, let me know and I will send you the PDF.
But
Now,
can you send your notes to Daphne and she'll put
I will do that as well. It's just I uploaded them last night, so
yeah,
there was no Daphne.
don't worry.
Yes. When I say late, I meant it. I did not.
Earlier than most.
So there will be homework problems. I tried here in the introductory. This is the first part, and maybe tonight there's going to be a second part. Who knows? But there are homework problems which are super easy, and I really advise you to do them because it will help you maybe get a little bit of more practice in these problems. Some of the problems will be requiring your computer. And again, you don't have to do them, but it will be good. Now, you can use any program you're familiar with, MATLAB, Python, anything, Mathematica, but I recommend, if you don't have anything that you're familiar with, I recommend Python, which is free. You can use the Anaconda distribution, which is open source, and it's very easy to install, and you can use these Jupyter notebooks that they have. And also there is a very useful module Network X, which some of the things you can basically do them with one line versus writing 20 lines of code. Okay, so my course will be about biological flow networks, and I am certain a lot of you have read many papers, seen many talks about networks. You've heard about Facebook, friendship networks, you've heard about gene networks, you've heard about airport connection networks, and you've heard all these buzzwords, degree distribution and node centrality and modularity and all that. Well, this is not at all what we're going to do here, and in fact the life here in any way is very, very different. Why? Because these networks are constrained in space. They're embedded in space, and because of that they have not exclusively, but that plays a big role, but because of that they have very constrained degree. Like each node connects to a small number of other nodes. They don't have, for example, hubs like what you see here. So in some ways these networks are much more boring than these networks. But I will try to convince you that maybe superficially they're boring, but if you look a little bit under the surface, they are absolutely fascinating. Now, why do we need a transport network, right, first of all? Now, I can assure you anything larger than a nematode has a transport network of some sort. You cannot find a complex organism in nature that does not have a transport network. The reason is that diffusion is very, very slow. This is very back of the envelope calculation for diffusion of oxygen in water. So to go 10 micrometers, you need about 30 milliseconds. 100, you need about 3, and 1 millimeter, you need 5 minutes. So yes, inside the cell, you could argue you don't need a transport system, although there are transport systems inside single cells. A nematode is marginal, but for a mouse, forget about it. There is no way you can build a mouse without a transport system. And in fact, the distance between the capillaries, which is the smallest vessels you have in the body, is such that the metabolism, which is basically like the rate of consumption of oxygen, is satisfied by diffusion as the oxygen basically diffuses out of the capillary. So this is consistent with that. Now, the transport networks, biological transport networks, are not only for the transport of substances, which could be nutrients, oxygen, etc., but it could be also for defense. As you very well know, when, for example, you cut your hands, or like this immune factors, right? You get an infection in your ankle, the rest of the body needs to know that something bad is going on there. Then another very, very important thing, whole body integration, right? So you're a child, you need to grow, you have hormones that are being produced in your brain, the rest of the body needs to know about it. Then regulation of heat, right? Ultrafiltration, but also, and this is perhaps, we're not going to discuss anything about this, but it's perhaps the most fun one, is hydraulic force generation. So you see all this fancy stuff about soft robots now, and we think that we're the first to invent it. Well, nature did it first and did it before it was cool. As mollusks, right, and this type of animals, they have basically a fluidic network whose not only, but one of its primary purposes is to move them. The motion of worms is another thing. So, told you this very, very general story. Now I want you, if you don't care about that, but you care about very practical things that keep us alive, this is a very broad sketch of our own human circulatory system. Again, this is stuff that I'm sure you've seen, but it's good to see it, right? So we have in our circulatory system, basically, we have the heart, which is a pump, right? And it spends energy to circulate, to push the blood around the body. So that blood, basically the oxygenated blood that comes from the lungs enters the heart, gets distributed to your body basically, where it's the nutrient and oxygen exchange happens, and then the oxygenated blood comes back to the heart and it gets sent to the blood to get oxygenated and back again. So that's the very simple story. But it's not the end of the story, because you have to worry about how much work this pump needs to do, right? And what's the distribution of pressure. So you start at the aorta at a very, very high pressure, right? And then that pressure goes down, and then the biggest drop, and we'll come back to that, happens around the arterioles, right? So you have the aorta, artery, and these are the radii. You can imagine let's say the biggest vessels. The aorta is maybe, let's say, around 1 centimeter, ballpark, and then the capillaries drop down to below 10 micrometers or so. Now, around the arterioles, which are roughly between 5 and 20, 30 microns, you have the biggest drop in pressure. This is the most resistive. Okay, so the blood starts on the heart, the pressure continues to drop, and then as it enters the heart, let's say it's at the minimum pressure. Now you're going to ask me, there's a problem, right? You have the heart, but also if the blood is right at your feet, then you have this extra pressure gradient that you need to overcome. So in addition to the heart, we and other organisms have specialized mechanisms when the pressure provided by the heart is not enough. So we have these valves, and actually the calf muscle acts like a pump with the help of these valves, and this is what helps propel the blood forward, upwards. That's why they say standing is bad for circulation, but walking is not, because of this mechanism. Now I focus too much on us, but the story is much, much, much cooler, because as you know, this colloquial saying, if it is a remote possibility that biology could have made it, biology actually did make it, and this is the story for animal circulatory systems, right? So there, any possible design and form you can imagine, nature has made it. So you have land and sea mollusks, you have crustaceans, you have insects. They all have very, very different systems, which could be open or closed, right? In our case, we have a closed circulatory system. The fluid never exits the circulatory system. But for example, the lobster, there is an open circulatory system. So the equivalent of blood that a lobster has gets basically dumped into cavities, and then it gets reabsorbed into the venal system and back to the heart. Now regarding power generators, right, how do you make the flow go around? you could have hearts which is or which could be 4-chambered, 2-chambered, 1-chambered. That also exists, which you could have in both open and closed circulatory systems, or peristaltic pumping, which actually I think it's only seen in closed circulatory systems. And peristaltic pumping basically is when the vessels themselves, they contract and expand and contract and expand, usually in a coordinated fashion, and they push the flow. Or maybe my favorite is cilia. When you don't have a pump, what you do is that you coat your vessels or your the container of the fluid you want to move with cilia, and then you beat the cilia and the fluid moves. And in fact, this is very common in our own body as well, in various organs. When you don't have an established pressure difference by a power generator, you do that with cilia. Now these are just two, let's say, test cases, which I'm sure you've never think about when you see these guys. The lobster is this guy here. It has a single-chambered heart and an open circulatory system, whereas the worm, which maybe to some of you looks equally boring like the lobster, it has actually a closed blood circulatory system for the global transport, but it doesn't have any heart. It has contractile vessels, which are like mini hearts. And also, on top of it, it has another circulatory system, which is called the coleomic circulatory system, which is for local transport around the organs, but also for locomotion. It's like it's a fluidic robot, although it is unfair for me to call it a robot, given that this came first and the actual robot second. Now I'm going to completely switch gears and tell you about something else that also has a circulatory system, which in my opinion is even more interesting than the animal ones, and these are plants. Now this is a tree, and that tree, as you know, sucks water at the roots and brings it to the leaves, right? And why this happens, right? Because at the leaves you have transpiration of water. Now there is no pump pushing things upwards, but water is being sucked upwards. So what you have here is a negative pressure. So the pressure up there is negative. That means that this column is under tension, basically is being pulled. What this means is that the smallest injury to the trunk of the tree would pull air in and will interrupt this water column. Now if you think this is an easy thing to do, then try getting a straw that is not 10 meters long, but maybe a very, very thin straw that is like maybe a meter long or like 3 yards long, and try sucking water through it, and you will see how hard it is, right? But plants do it. Now what happens at the leaf and why there is all this continuous water loss is that the plants need to photosynthesize, and they need to exchange gases. Now the leaves are protected from complete dehydration through the epidermis, but to exchange gases you need an opening in the epidermis. These are the stomata, which you remember from your high school biology. And when the stomata are open, you photosynthesize, so oxygen gets in, CO2 comes in, oxygen comes out, but also accidentally you lose water. And by the way, plants are hugely, hugely inefficient in how they handle water. They're extremely wasteful. I guess biology didn't find a better way to do it.
So how do we know that?
That they lose so much water. You can do this by a lot of very fun experiments, where I think the most primitive experiments they did without any equipment is that you take a plant, you water it, then you make sure you don't have evaporation from the soil, you wait, and then you come back after a few hours and you wait again, and all the mass, all the weight that is missing has to have gone somewhere, right? And it's water, it's massive. And they're much more sophisticated experiments than this, but that one you can do at home. And you can also see that if you just take a potted plant and enclose it in a plastic bag, it will be full of vapor afterwards.
How about plants in deserts, for example? Because there they have this
Yes, excellent. So Yes, they have a lot of, these plants, they have a lot of mechanisms to improve that relationship. So they are adapted to that, and they're very, very good in not wasting water. But these mechanisms don't happen here, right? So the plants that actually, it's unfair for me to say they did not evolve something better. They didn't actually need it, right? If they needed it, like the desert plants, they would have evolved it, to be honest. But what happens is like in a regular temperate climate plant, you have a lot of water loss, and basically that water is replaced. It's replaced by that water that comes up the water column. And then of course there is the phloem. We're not going to talk about this. The phloem is what takes the sugars back to the rest of the plant. That is different story, which is very, very much more complicated. Now, this is what you would see if you took a leaf and you cleared it and you stained it, and you can see it has this very complicated venation. But then if you took a microscope and you looked at the xylem vessels, you would see all these complex mechanisms. And then this is a cartoon, because you can't really see it very well in the micrographs. This is, let's say, a cross-section of a plant vessel. And you will tell me, this is, as we will learn later in the course, if you think of this naively, with the very simple models we will be doing later, this is an insanely stupid mechanism to do this, because you have the water flow. First of all, you took a big pipe and you subdivided it into many smaller pipes, but on top of it, you went and you put these things that are called sieve elements, if I remember correctly, that basically add resistance to the flow. So you're forcing the water to go through a very circuitous path up. Now, why do the vessels in plant have this insane design? The reason is what I told you earlier, is that since this water column is under negative pressure, if you have a little injury here, you will have air coming in, right, to fill the hole, basically. And what happens is, although if you measure the actual pressure difference between here and here, this air would like to enter, because this has negative pressure, this is atmospheric, right? For the bubble to squeeze in through the little hole, it needs an extra pressure difference because of Laplace, right? Because it needs to bend a lot. So plants have found an ingenious way to take advantage of basically simple physics to protect themselves from incidents like this. Now, why did I show you all this? I showed you all this in my long and circuitous introduction to make you aware that things in biology and in this seemingly simple vascular networks are actually very complicated and very interesting, each in its own way. And then I will go again one step further, and I will talk about rivers, and you'll tell me rivers are, what do rivers have to do with anything? Well, they are a flow system, and in fact they obey scaling relationships that are eerily similar to the scaling relationships in our own circulatory system. And in fact, we're not the first to notice that. Da Vinci also was very interested in this, and he made the analogy, he wrote like a beautiful text making an analogy between our own blood flow system and the Earth's rivers. Of course, he didn't know about actual the scaling relationships between flow and conductance and all that, but anyways. So now another thing I want to, before I finish this PowerPoint presentation, another thing I want to make you aware of, which is actually important to keep it in the back of your mind, is that you need different models at different length scales, right? So this is the textbook view of our vasculature. We have the arterial tree joined with the venal tree, right? And this is when you look at it at like the large scales. When you zoom in, you see more or less uniform capillary system. It's in neither extreme it is so clean. So you have some loops here and you have some tree-like systems and hierarchy here. It's a very, very complicated story. And the worst part is that the models that you would actually need to use are different at each scale. So you have to be very careful in exactly what you are calculating. So up here close to the heart, the vasculature is more tree-like, and the flow is to a large degree non-laminar, and it's pulsatile. You can really feel the heart beating. Now, as you go further down, you get many more loops. The flow, you can model it as laminar, much more confidently, but then the viscosity is not exactly constant, and this is because the fluid is complex and you have blood vessels that are floating and doing their own thing, etc., etc. Now the pulsatility decreases, but you have to remember that the vessels are covered by muscle that actually dynamically controls the diameter of the vessel. Then you move to the other system, the veins, and you have the capillaries. When the flow is, yes, it's laminar, but then the vessels are about the size of the capillaries, so they have to squeeze through the capillaries. So that means when a capillary, when a red blood cell is through a capillary, the conductance of that capillary actually changes by the fact that the vessel is in it. So extra complication. And then you have minimal pulsatility there. Then when you return here, the picture in some ways looks like the artery is close to the heart minus the pulsatility. As you know, you can't really get your pulse from your veins, right? Only from your arteries. So with this, I hope I've made you aware of all these complexities, and now we're going to go to this stuff. And I can assure you it's not hopeless, right? We can compute things, and we can try to understand general organizational principles of these networks. Now we're going to do, I promise, we're going to do the absolute simplest thing, and we're going to talk about linear flow networks, right? You know, you're in physics, you know the simplest approximation you can do is a linear approximation, so this is what we are going to be doing, and we can go pretty far with that alone. So I will disconnect this and get to the blackboard. Okay. And all my notes are in here. So I hope this doesn't die, because then I have to go like free form. Okay. So, and again, you don't, for the most part, you don't really need to get serious notes, because it's in the notes that are online. Okay, so I'll first start by drawing a simple network. If the ones in the back cannot see it, it's too small, let me know. Okay. So this is a graph. A graph consists of a number of nodes. Let's say in this case, okay, so we have, let's say, n nodes. In this case, I think it's 6, and m links, which in this case is also 6. Okay, and we will be representing, let's say, the edge Eij, which belongs to my set of links squiggly E, is basically the edge that can be represented with this ordered pair, right? This is important that it's ordered. You see, I've drawn here some arrows. The edges in what we will be discussing have a direction. So the edge 2, 3 is the edge that goes from 2 and 3, is the edge from node 2 to node 3, right? Now this is different than yes, I should have called them, sorry. I said directed, but that was I misspoke. So these edges are oriented, but the if you have a graph with oriented edges, that's not the same as a directed graph, right? There is a small distinction there, because let's say a directed edge is like it's like a vessel with a valve, right, that only allows the flow to go one way, but an oriented link means that actually we have prescribed an orientation to it that eventually, as we will see very soon, will give us the sign for the flow. But yeah, we'll discuss about this later. Now, you see there is a relationship between my edges in my graph and my my nodes, and that relationship can be represented by an incidence matrix. Okay, and I will denote this incidence matrix with this delta hat t, and keep in mind that there is a t here. It looks like a transpose, and we'll see what that is. And if my let's say if my edges in this graph are as follows. Now, if I just look what I write, if there is a typo, and I messed up one of the orientations, you should let me know. But let's say I have these 6 edges, and these 6 oriented edges, I can write down a matrix. We broke this, so I'll go here.
So, I mean, does it matter what we should do? You're really thinking about these vascular flows?
It matters very soon.
Okay.
You will see why.
So we should be thinking about vascular flows, blood vessels.
Yes, because I haven't, this doesn't even have a field on it yet. So this is my incidence matrix. And that incidence matrix basically is a matrix which is n by m. So it has n rows and m columns. And basically tells me who is connected to whom. I'm not going to write down the whole thing because you can see it in your notes. I'm just going to write a few examples, a few of the columns. Okay. Now what this means here, right, is that this is the first node and this is the first edge. that means that the first node participates in the first edge as the part of the edge where the direction comes out of. Okay? Now, right here, as you can obviously see, this node 2 participates in edge 1 as the incoming node. And from this you can obviously see that if I take the incidence, this incidence matrix, and I sum it along the columns, basically I sum all the rows, that should sum up to 0, right? Okay, so I have this. Now, what I can do to go back to Alex's question is that I can go and I can put a flow here. Okay, and I will redraw the same graph, a little bit different, because now the edges are gonna have weights. Okay, maybe I'm gonna make this fatter, this thinner. Okay, and Q2. So the arrows here is the direction of the flow. Okay? Now, that flow field Qij is basically, if this was a vascular system, how much flow is going to go through the pipe, basically how much volume per unit time. Now, this obviously, because you know flow can go this way and also can go that way, I have to choose what is my positive orientation. And now if the flow is going according to the direction of the oriented edge, then that flow is positive. If the flow is going against the oriented edge, that flow is negative. So I can define this as an n by n matrix, right, which is actually antisymmetric. Okay, and also I have something else interesting here, and that is that at each node I need to have mass conservation, right? So these are the flows Q, K, I are the flows that go from K to I. So if I sum up all the K's that actually point to the node I, with the sign being taken care of properly by my original conventions, then that should sum up to 0. That's mass conservation. That doesn't need to happen, right? If the node is a leaky node. So I can define another field now, small q, and this is called the net current. This small q, actually, as I drew here, actually lives at the nodes, and this is how much this balance is basically if you have a net positive of fluxes coming in, this is coming out. Again, this is very simple, is mass conservation. Now, there is some fun here because you can very easily see, why did I write down this guy? You can very easily see that I can write down this relation in a very compact form. Now I can take all these Q's, I can write all these Q's as a matrix, right? As an n by n matrix, but I can also take all these Q's. This Q's is a field that lives on the edges. I can go and I can write them as a vector where basically the first entry of the vector is the flow in edge 1, the second entry of the vector is the flow in edge 2, and so on and so forth. And if I do that, I can write my very simple conservation equation in a very simple form, right? Very, very concise form. Okay. Now there is something other very interesting thing that nobody complained about, and that is, why did I write, so this is a small digression, okay, which is a math digression. Yes?
I think the dimensions in that equation don't work out. Q is an n by n matrix and delta
Yeah, so here? Yes, good. Thank you very much for the question. So this one is, that is, I didn't write enough on the board because I want to tell you a lot of things, so I'm hurrying up. So now this capital Q, perhaps I should add it here. This capital Q is an m by 1 vector. You see this had the hat over there, it's an m by n, it is an n by n antisymmetric matrix, but this Q with the arrow on top is actually a vector which has the following entries. And two more that I cannot fit. You see, so now these dimensions fit. I wasn't very clear when I wrote this quantity there as a matrix, which is simpler to understand, and then I wrote it as a vector. But this is, you will see in the next 5 minutes why actually this is very, very cool. Now this is, it's a high...
Define Q based on your graph.
That's exactly right. So I define Q. I didn't have, you need 2 more entries here where there is no room. But I have defined here my list of edges. And I can write them, actually, I can write a vector, right, that has the dimension m by 1, where the entries are going to be whatever field lives on those edges. So this is...
For example, just to be clear, when you have 6, 3, I mean, does it matter that it's Q 3, 6? Or
It does, yes. If I want to do it differently, if I want to use the 6, 3, then I have to put a minus sign in my flow to be consistent, right? So when I write this here, this list, which I wrote all of it, establishes the sign convention for the flows that comes from here, from the orientation of the edges. And then that is carried everywhere. It affects the incidence matrix, and it affects this vector here, where each entry is, there are m entries where m is the number of edges. And these entries basically tell me where how much flow you have on that oriented edge.
But it also seems to me that it matters if you put, say, Q, what was it, 4, 5, and then 3, 6, or you first put Q, 3, 6.
It does, exactly.
So
That,
how do you pick it?
perfect. So you pick it by convention. You're exactly right. So you see I numbered everything. I numbered my nodes. Here it's on this graph. And now I have also numbered my edges. So I have to use this numbering. Now everything is ordered and numbered and tidy. And I have to use the same thing.
So according to this, 4, 5, Q 4, 5 will come before Q 3, 6.
Q5, 4. Maybe I wrote it.
No,
No, maybe 1, 2, 2, 3, 2, 4, 4, 3. Yeah, I didn't write the rest too. The last two. You're absolutely right. Yes, that's exactly right.
And in practice, the vector Q contains the only non-zero entries of the matrix Q.
the vector capital Q.
Yeah.
That's exactly right.
And you have only given them an order, so you don't have to worry.
That's exactly right. That's exactly right. So perhaps I should not have written this statement, although it will be useful when you guys program, if you decide to write your own code. Perhaps I think this caused a lot of confusion. So it will be removed for now. Yes?
I had a question which might be related to it, but over there you seem to describe describe them as leaky nodes, but in the next equation they're leaky edges.
No. This is here. This quantity tells me at each node, perhaps how much current you are losing, you are leaking, right? Here, when you perform the computation here, when you perform the product, what this will spit out is a vector which is n by 1. So I'm summing up, and actually, if you wait a few minutes with your question, I'm going to have a small digression to show you something really cool that you don't really see it in physics so much, but it's super useful if you work with this type of problems or mechanical networks, flow networks. We're going to discuss this matrix a little bit, the incidence matrix. And I think that might help you with this. So we're going to do a small digression here, which are some cool facts. Now, this incidence matrix here, which I didn't write all of it, you can download the notes right now and you can see it in front of you. But that matrix there, you see, I called it incidence, and I had a delta and a transpose there. And this sounds highly suspicious why I used that transpose, right? Why didn't I just define it something else without the transpose? The thing is that matrix without the transpose is a very cool object when you do calculations in graphs. It's a boundary operator. I'm not a mathematician, but I would say as a physicist intuitively, it is the closest thing you can have to a derivative on those systems. So speaking of, you all know the fundamental theorem of calculus, right? So I don't want to be changing my notation. So, right, that's this very, very boring thing, you see. Okay, now this has a very, very fundamental importance both in calculus in its most general form, where people write like this, where basically you have the integral of a derivative, you have the integral of the derivative of a field over an orientable manifold, and that becomes basically the integral of the form itself, your field, over the boundary of the manifold, which is basically this, right? If you look what I did here, basically I have omega, which is the integral from a to b of something which is basically df, right? And that is equal to just taking f itself and calculating it on the boundaries. Now you'll tell me why you have been writing all that, and that you're trying to explain to us that the transpose of that thing over there is actually something that takes, it's a boundary operator on a graph, right? So I'm going to do a very simple example to demonstrate that. And my ultimate goal here is, guys, for you to be aware of some identities that help you do the equivalent of Stokes, Green's theorems, anything else like that, but on graphs. And these things are super useful for any calculations in linear fields. So I could do a graph that is now very simple. It's like this. It has 1, 2, 3, 4 nodes, F1, F2, F3, F4. Okay, so I define a field on these nodes. It could be anything you want, right? It could be my blood pressure along my vessels. And now I will write down my delta t for this graph, which is simple actually. Oops. Okay. No, that's wrong. It has an extra column. I got carried away. Okay, so you see this matrix has is n, where n is 4 nodes, by 3, where I have 3 edges. And now if I take the transpose of that, and you can do this algebra quite easily, if I take the transpose of that and I apply it to, yes?
So the flow is not going that way.
There is here, we don't have to worry about flow, but I should, you're absolutely right though. I should have oriented, thank you. If I had brought chocolate, you would be getting a lot of it now, if you like it. Yes, I made a major mistake. Yes, I should have, that's super important because I drew this without that. Now what I need to do, what I can do now is I can take this matrix, and I forgot its hat, and I can apply it on this F. And if you do that, then you get this, which is basically the differences between the edges, between sequential edges. Okay? So now I have, without writing any complicated stuff, I now have in a very nice closed form something. If this were the pressures or the voltages, I would have a relationship for the pressure drop between the ends of the links or the voltage drops. Now what I can say
So
is,
wait, just for notation, you're now writing, defining a delta F, or you're acting?
no, I'm not, I'm acting, yeah.
You're acting.
My handwriting needs improving. So now what I am basically trying to recreate is this relationship for graphs, right? Slowly, I'm just creating the elements little by little. So now what I need now is something for, in this particular case, what would delta t be, right? If I was integrating over an interval, it would be tell me this length and this length and this length and this length. So in my case, my delta t becomes a tau, which basically is once. And now what I can do is I can take this is basically the inner product, or you just multiply the two vectors, and I can do the algebra really quickly, and I can see basically if I dot this with this, which is what I'm doing here, I see that finally my final result is F4 minus F1. And you probably see where I'm going now. Right. Now there is another thing you can do though. Right. You can say, I will take the transpose and apply, I will take the transpose of the boundary operator, which is the incidence matrix, and apply it directly to this tau. And that will give me F4 minus F1. No, sorry, that's stupid. That will give me this. Okay? And now I can take So what did I do here? I took my incidence matrix, I applied it to this tau matrix, which basically told me how much, if I were to add up any fields that we're going to have in its line, in its edge, how much they would count basically. And I took the incidence matrix on that. I got this vector, and then I dotted it directly with f. And I got this quantity, which is this quantity. So what this means is that, and I guess I need a new board for this. What
so
this?
The delta T transpose times tau is like the long-term incidence effect, right?
I'm not
Did you
sure what you
interpret it
mean by that. So what do you mean by that?
I mean, it's just at the long run, what's going to be the output of the network or something like that?
So the best way, I wouldn't think about this like that. I would perhaps think about this as it's a little bit like a derivative in some way. That's perhaps the best way to think about it. Because this network doesn't really do anything yet. I haven't asked it to do anything. This is just a simple statement. You take this delta, you apply it to F, which is any field that lives on the nodes. Then you take the inner product with something that gives you basically the, this is a vector, this tau is a vector which is m by 1, right?
Is tau always the unit vector? I mean, just a vector of 1.
That is a good question. For the particular applications that we are doing, because we're using basically as something that eventually, if you want to turn a summation into, a vector inner product, then you need to apply, right, this has to have weight 1. If you don't use weight 1, then other things happen that we don't need to care about right now. So let's say, for what we'll be talking about, and we're not going to get into much trouble with this, it's yes, let's say yes, to make it simple. Yes?
Can you formulate something more abstract terms? So like what are you trying to do? Like,
Yeah. This is where.
graph,
Yeah.
you would like to define like the operation of taking boundaries, then like you're
Yes. I'll come to that. What's the purpose of this? That's what you're asking.
like abstract terms because like all this stuff like
Yes.
the big picture.
Yeah, exactly. The big picture is that the big picture is that all the stuff, all the theorems that you know from, all the stuff that you learn from calculus, actually, not all, but a very big chunk of the stuff that you learn from calculus that are super useful, like relationships in E&M, where this, right, you know this from E&M, right? This also applies to graphs. This is what I am working towards, and this is a very, very small manifestation. And this is very useful because this relation, and perhaps we should do it as an exercise, this relation, if you apply it right there, it tells you something about constraints on the queues. This is what the purpose of this exercise is, basically show you something that is really, really cool. So this holds true, and this holds true in every graph imaginable, right? Yes?
This is a little big, but are you trying
we're not there. Okay, maybe I can try to show that what I think
Like
is
from
going on, right?
Just from this correlation, sorry.
I think so far Eleni is just trying to teach us the basics.
The very basics, yes.
Calculus on graphs.
That's right.
Because there's rules, there's useful relationships, and if we want to then try and actually calculate something on the graphs, we need to learn what they are, and that's what
That's
we are at
yes.
this point. So
This
we're
is
not
the
talking
yes.
about
This is basically stuff that do not only apply to flow networks, but there are. You can think of what these things means for flow networks, and in fact, if you want, what I will do is that I will recast everything in flow network terminology, so you will see. Yes.
That matrix basically means, I mean, that expression basically means that it's a linear form, right?
Yes, basically. So this is, yes. But again, then let me actually go to make things very specific then. Let's say this, I'll call this pressure now. Okay? These are pressures. And I don't know much about the network, but I want to calculate my pressures, okay? So I can do this like this. Okay, now I have the pressure differences along its edge, which is super useful. And then what this, you don't need to do anything for your notes, right, for this. But if I go back here, this would tell me that if I were to go and add in this particular graph all the pressure drops between the edges, because the graph has this very, very simple form. This is like a chain rule, and in the end it would be the same as getting the pressure at the leftmost node and subtracting from it the pressure at the rightmost node, which is the same basically as taking the boundary of the graph basically this way and dotting it to the pressure, if you ever wanted to find, to calculate something like this. Now, why this is cool? Because the graph can have any complexity you want, right? And this is not only because the graph has this chain, it looks like a chain. This is very, very general. So you can do it for any graph. And this type of relationships allow you to take very, very long, as we will see very soon, very, very long expressions that you can prove using summations and indices, and just do the same calculation in just half a line.
So any graph, you really mean any graph? Like, is there an exception? Is there
So
loops are okay, clearly?
yes, and I mean,
Can any graph? Any graph we'll ever think of.
any graph, any
I'm just
graph
trying to-
which has, yes, so I'd have to, if you can't have, you can't have things like that, obviously, right? Right? But other than that, I would say yes. Maybe there are, but any graph that would be relevant for flow systems,
Okay, so
yes, and this you wouldn't,
Right, okay, so any graph
would
that
have more
has,
nodes, yes.
flow in one direction on an edge, basically.
yes. And then also, yeah, I don't know about stuff like that. So I have the disclaimer, I'm not a mathematician. So if there is a mathematician in the audience who is an expert on this, they should come and tell me. But for the graphs that we're going to be using, to the extent that we're going to be using them, this is, yes, what's happening. Now, we have so far, and it is after 10 already, we have established, let's say, the very basic toolbox of what we were going to be needing. And we have a few extra things we need to worry about, and that is, we need now, let's say, we have a way to put fields here, on the nodes, and this would be our pressures, right? And we have a way to put fields on the edges, and these are going to be our flows, but we need to connect our flows with our pressures, and that is, you can kind of get this very simple relationship from first principles. But this is what it's going to be like. So the flow that goes from edge, that goes through edge ij, right, is, I'm going to write it like this. So the flow that goes through edge ij from I to j is proportional to the pressure drop between the ends of that edge times a proportionality constant, which is the conductance. So the larger the conductance, basically, the more flow you can have for a certain pressure drop, and the smaller the conductance, the less flow you can have for a certain pressure drop. Now, with all of the machinery we were building, we can do things quite easily, right? So I can define a matrix, which I will call it diag C, which is a very, very simple matrix. Oh, what am I doing? That's wrong. So it's an m by m matrix, and in the diagonal it has the conductances for each of these edges. Okay? And 0 everywhere else. Okay? That's very simple. So now what I can do is that I can write this relationship from my entire graph like this. Okay? And I will pause for a moment so that you can see it. So now what I've done is, instead of just writing this m by m times, that relationship n by n times or wherever times as needed, I can just write it in matrix form. This here, when this matrix delta hits on this pressure at the nodes, then, as we were discussing right here, I get the voltage drop or the pressure drop along its link. So I have that part down pat, and then I multiply it with this diagonal matrix, and I get the flow. Simple, right? Good. Now I will digress a little bit. This is only a tiny bit, because you will now ask me, so how about this relationship? Where does it come from, right? Some of you will say this is the absolute simplest thing you can do. It's just, you can have a more complicated relationship. You could have Qij equals a function of delta P times Ci, just a general function of delta P. And then you just do a Taylor expansion and you keep the linear term. Okay? There is a case where this is, let's say, exact. and that is Poiseuillie Flow. Now, this is something that quite a few people now learn in grad school. So who has never heard what Poiseuillie Flow is? Okay, so I'll, okay, then I'll do it.
So can I, since we're going
Yes.
there, if I think of a pipe
Yes.
and I think of general fluid mechanics,
Yes.
there's an equivalent of this, no?
If
Right?
yes, I mean if you can if a linear approximation is a good approximation, then that works. If there is time in the end of the course where there's not going to be, we can see what happens when that's not linear, and I can tell you really, really, really cool things can happen if that
Can you
relationship
just,
is not
I mean,
linear.
For those of us who have seen this but have gotten Alzheimer's, can you write down the sort of classical fluid mechanics equivalent of this equation?
I was going to do that right now. That's as you say, this is at the next slide. That's exactly what I'm going to do. Because this is, if we're going to be talking about laminar flows, it would be actually very useful to be able to say what that conductance is, right? Yes?
I have a question about interpretation over there. So, for example, when you were taking the boundaries and you were taking the dot product, suppose I had a node without any outflows and you only had inflows.
Yes.
So, in that case, what does the inner product tell you?
You mean, yeah, so first of all, sorry? I didn't.
That you need a plumber.
Yeah. No, actually, no. I would say, because I'm a theoretical physicist, I would say that if it's all accounted for in your equations, you have nothing to worry about. So as I wrote it right here, right, you see the fields I have written down all live at the nodes. I haven't explicitly discussed any flows. I was going to say, translate this to the relationship I think I wrote earlier, which is this, right? And I think this is perhaps what you are referring to, but I decided against it because it's already 10:15 and I'm not even halfway done. So perhaps if you want the easiest interpretation is for, let's say as an exercise, you can try to take this and think what this means if you apply it. I erased it. No, it's here. If you apply it here, right, you can see what you can tell if you take that and you try to apply it here. But before we do that, this basically tells you what this operator here is doing is just keeping track of the proper orientation, is summing up all the incoming flows to each node and saying, well, those incoming flows have to be equal to the net currents at their links. So this could be absolutely zero and you would be fine, right? So this is what this is actually a very good question because it is at the heart of what this thing is doing here. The transpose of the boundary, the incidence matrix. It just takes all the nodes that are incident to a particular other node and then goes and finds the flows there and adds them up.
So you're saying basically they would end up at the nodes. You'd get some sort of arrows, like steady, in his example. Like if I reverse P4, the Q34 now and I make it -1?
Yes, excellent. So you're right. So if I had, perfect. Now I see that. Thank you. I don't think I misunderstood the question. So let's say you had, these are the orientation of my edges. Okay? This is the orientation of my edges, but then my flows go like, my actual flows go like this. So you see this is opposite. Okay, is this related to your question, or I am?
Maybe I don't know yet.
I think all he
The question was
wants.
about sources in your system.
I think my understanding of this question is Avanish wants this, right? You want a network like this, where you can't.
Ah, okay, that's fine. Oh yeah, sorry. Okay, thank you. Okay, then let's do it. Easy. And in fact, I'm going to do it with the same color chalk. So that will make that happen, right? So let's see what happens, because I don't know. Okay. So then what will happen here is that this will change. Okay. And what will happen here is that I will have this will change. So I guess I don't need to write. It will have some extra terms. It will have 2f3 minus f1 minus f4. Okay. And then if you do it right here too, which is perhaps is gonna answer your question, then you will get. Need an eraser for this. Okay. So basically now, because of the orientations, the inherent arbitrary orientations you have chosen for your system, the outcome, what you calculate if you do this identity, changes as applied right here, but this still holds, obviously, and you can see this by how this changed. This identity still holds, but also this holds again. Everything holds. If you do this consistently, everything holds. And I changed this orientation. My incidence matrix changed. Now, if I keep track these Q's is what they tell me where the flow goes and what the flow does. And if you take it into account properly, you still get the exact same relationship here, right? That connects this quantity with this quantity. Here I have applied this. This also still holds if you need to do this calculation. Yes?
Just to make sure I understand, there are two things on each edge. So the orientation, which is something you choose by convention.
Yes.
Say, and the actual flow. And if you have sources of sinks or sinks, this will reflect on the flow. Say. Right?
That's absolutely right.
So, but the orientation of the edges, does it
You
have
set
any
it by hand.
physical- Yeah.
No.
It doesn't have any
No,
physical-
it is for bookkeeping.
Okay.
Because if you don't set what somehow you have to set what orientations are so that you give your Q a sign.
Yeah.
I mean, and if the Q that you calculate happens to go opposite to the imposed orientation, that is a negative sign, right? This all will become more clear when we actually start using it to solve, like I would be giving you the conductance, and then you would be calculating everything else from the system. Yes?
I have a question about the interpretation of this tau, so this vector.
Yes.
Because so depending on how you number them, it seems to make something different.
What do you mean how you number them?
Or in which direction basically you have the edges oriented. Because so if you look at the last equation,
Yeah, so perhaps I it would have been easier if I did this in just in much more practical cases. I would say do not, so that we move on, I wouldn't worry too much. So if you do everything consistently from the beginning, right, as you do these calculations, the intermediate things change how they look, but in the end, your final result shouldn't change. This is all what I'm trying to say. So here, I am not sure what you mean by the interpretation of this tau. So what you can do if you like to be consistent, nobody stops you from using something else for tau, right? If you do this change here with the brown chalk, and perhaps you should try it. If you do this change with the brown chalk, perhaps you can also go here and say, I will multiply whatever I see there with a -1 sign, and then you will see in the end things will be reverting to the original result if you do that, if you decide to do that.
But so depending on how you chose like the orientations, you would choose different tones.
Yes, and again, this is all, yes, basically, because this is referring to the default orientation, but you could do that, and if you do that and you proceed there, you'll see what's going to be calculated here is the same, and what's going to be calculated here is again a 4 minus 1, and they're still consistent with each other. Yes?
So how should I think about the difference between what you're calculating? Like if you choose one tau or another tau, what is it?
So again, this is if you are consistent, and this, you see, you can put anything you want here,
So
right?
I think, okay, you're telling us...
You don't have to, right now, don't think about physical interpretation right now.
So your goal here is to just show us the equality between the
This.
two differential forms. And
Yes.
we should not attempt
Don't
to
worry.
interpret what the differential forms give.
Yes, because depending on what you want to calculate later, we haven't really told you anything that you could be calculating on this graph, 0 yet. So it's difficult to talk about interpretation without actually having talked about any fields that are relevant for these graphs. That's the whole thing here that I'm trying to say. Yes.
Do you think you could do this within the next 5 minutes? Which is
I was gonna just write the basic thing for Poiseuillie Flow,
okay.
which is fairly quick, and then we can end.
Next time we move on.
Yes. So basically, right, perhaps I could start this and then we'll continue tomorrow. So let's say I have a flow in a pipe, right, which goes this way. So this is y, this is x, okay? And what's happening is that that flow that goes along this direction changes along the y-axis. Okay, so you have more flow going at this height and then less flow, or the velocity, I should say. You have higher velocity here and lower velocity there. So there is friction between these two layers, right? Okay. This is, let's say I have these two layers, and if the top one is going faster than the bottom one, there's going to be a force, right? That's a frictional force between the two layers, which of course is going to be proportional to the contact area between the two layers. Now what happens if you have a cylindrical pipe? Yes?
Is it U alpha actually Vx?
Did I write? That's,
And this is the same V.
it's the same V, yeah, it's my, thank you. better now. Okay, good. So if you have a pipe basically and you're trying to push flow through it, then what happens is that here at the boundary you have no slip, there is zero velocity. But here you have the maximum velocity, right, of the flow. And then you want to calculate what this profile is, or eventually if you have a pressure difference here and here, right, you want to calculate how much flow you can get for this delta P. So this is how you get it. You can look at the details at the notes because I'm running out of time, but basically the way to do it is to consider basically that you have this layer here, right, and this layer is being in a way pulled by the layer at the top, but then dragged behind by the layer at the bottom. So you calculate these two forces, and then you subtract them, right? And then you have to keep track of this. You have to keep track of the fact that because you're in a cylinder, the area of the interface changes as a function of the distance from the axis. And in the end of the day, you get that the pressure depends on the velocity like this. And you see the two derivatives come from the fact that you have to subtract these two forces here. And you have one derivative from here and one derivative from here. Okay, now what you can do further is you can solve for the velocity here, and you can find the famous parabolic profile. So the flow has a parabola. And then the next thing you can do, obviously, is to calculate the total flow by integrating. Okay. And algebra, in the end, you get something which is a very, very important relationship, which you will have memorized by the end of the week accidentally. And this relationship tells you that if we have simple laminar flow, okay, the pressure is proportional to Q, and the conductance that I introduced earlier is proportional to the fourth power of the radius, or the area cubed. This is the conductance of a flow pipe of a radius r, right? So this is super, 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 super important for our own bodies. It has implications for how our vessels scale. Like if you have a vessel that is bifurcating, there is a relationship that is depends basically on this. So this conductance proportional to r to the fourth, it will be, you know, you will be disgusted by it by the end of the course. So now what we've done so far, and I am out of time, is what we have learned in this course is some very basic things on how to write down a graph and define things on that graph. The fact that one could do cool things on that graph with calculations that we didn't get into details because perhaps it was premature. And the last thing that we did is that we have established that in linear flow networks there is a constitutive relation that means something, that Q is linearly proportional to delta P with a proportionality constant that we know. And next time we're actually going to start calculating things, more complicated things on graphs.